Okay, we have another problem for physics from the electromagnetism section of a university physics book, and the problem is going to be, and it will be listed in the description below the video. You can read it there. I'm going to read it now. A straight non-conducting plastic wire 8.5 centimeters long carries a charge density of 175 nanocoulombs per meter distributed uniformly along its length. It is lying on a horizontal tabletop, and we have A, find the magnitude and direction of the electric field this wire produces at point 6 centimeters directly above its midpoint, and B, if the wire is now bent into a circle lying flat on the table, find the magnitude and direction of the electric field it produces at a point 6 centimeters directly above its center. Okay, so let's think about the problem first here. It's not too difficult of a problem if you know how to do the midpoint in this situation for an electric field. So we want to find the field for such a wire a distance x from its midpoint. Usually what's good here is instead of starting to take equations and plug numbers in, that we get the equations and we build them and then plug the numbers in. That way, we just build them using variables, and then we know that the equation's correct. Then we just plug everything in the calculator, and that'll give us our right answer. So first off, let's see here. So E is going to equal 1 over 2 pi epsilon naught times x square root of x over a squared plus 1, and then lambda up here, and that equals 2 times 1 over 4 pi epsilon naught times lambda over x square root, same thing, x over a squared plus 1. So if you look at this equation here, you should be familiar with these things from reading the textbooks and everything. In this problem, I'm not going to go into detail on the definition of this, because we're at a problem where if you're doing this problem, you should be fairly familiar with all the equations and how to get to those. If you're not, then I would go back and get familiar with them. So you can see normally we use 1 over 4 pi epsilon naught in our electric field equations and our Coulomb's law equation and everything for finding the force and stuff. So we're looking for a midpoint, and we're looking for a midpoint from the wire. I believe here it was, say we have a wire, and then we have a spot up here above the wire, and we want to find the electric field at that point in the middle of this. So the wire is emitting an electric field, in a certain direction, and we want to find that stuff. And so this is for the midpoint, and then so we take this here now, and we're going to plug in all of our numbers that we have been given for this problem. And so we have E is going to equal going to be 18 times 10 to the 9th newtons times meters squared per coulomb squared, and multiplied by, make an extra line here, 175 times 10 to the negative 9th coulombs per meter, and that's divided by our distance that was 6 centimeters for x that they gave us, and so we want to put that in meters, 0.600 meters, and then times the square root of 0.0600 meters for our x value again, and then the a value was 4.25 centimeters, and so we need that to be meters, so that's 0.0425 meters, and that's squared, and that's plus 1, and that's under the radical there. Okay, so now we solve for that problem, crunch it into the calculator here, and that comes out to be 3.03 times 10 to the 4th newtons per coulomb, and it is positive, and so it is directed upward. And so that is the answer to part A. And for part B, the answer is going to be here. This is going to be a little bit more work here. So for this was part A, and we have part B now. And so for part B, the field is caused by a uniformly charged circular wire. So the field for such a wire, a distance x from its midpoint, is going to be E equals 1 over 4 pi epsilon naught, and multiplied by Q x over x squared plus a squared to the 3/2. And so if you know, these equations can be relatively assumed. If you wanted to work them out, we got a circle here, we've got a point, and we've got a right triangle from the center to the point to this, and so if you get you see x squared plus a squared, well, this is the radius. We're calculating the radius here, and we're using Pythagorean's theorem to calculate that, and from here to here and all around and everything. So you can figure that out on your own, in the midst of a problem. And this is this is over 3/2, and so it would normally be r squared, and so there's other things involved when you're putting it together. But in this case, we'll just take the equations for granted from the books and stuff, and if you're asked to derive it from graphing and all that, or drawing a free body, I mean, you should really know how to do that kind of stuff, because you'll get some more difficult problems if you're going into physics or math. If you're going into engineering or some type of other science, then probably not as important. So the field for such a wire, a distance x from its midpoint, is this right here, and then we first find the radius of the circle using 2 pi r equals, say, L. So 2 pi r is equal to L. That was a horrible L. And so solving for r here, we're going to get r is equal to L over 2 pi, and we were given the length, and that was 8.5 centimeters. So we'll get 8.5 here centimeters divided by 2 pi, and that equals 1.353 centimeters. Okay, now that we have that, and the charge on this circle is Q equals lambda times L there, and that equals 175. Remember, this was given to us, nanocoulombs per meter, and times our L value, which was 8.5 centimeters. In this case, we need to convert it to meters. This is okay here because that we were dealing. We'll convert that later if we need to, and we probably will need to. But in this equation, it's okay. You should be able to recognize when you can do that and not do that if you're in this level of physics. So you should have learned that from your first semester, and that equals 14.88 nanocoulombs. And we're going to have to convert the nanocoulombs into regular coulombs as well. So again, in this equation, it's okay to do that. But when we plug into this equation up here and we get all these other variables in here, everything needs to be in system international units, which is meters, kilograms, and seconds. There's no time in this one, but okay. So let's continue on with this problem here. And we've got, now that we have our Q and we have our R, we can start working this problem. And R is going to be, in this case, what we solved for R here was our A right here. So just try not to. You could have used R there, whatever you're used to using, whatever makes you feel comfortable and happy inside when you're doing these problems. So let's look here. So E is going to equal this equation here, and so I'm going to go ahead and plug that in. And now we know that 1 over 4 pi epsilon naught is equal to constant K, which is equal to 8.99 times 10 to the 9th newtons, or you can just say 9.0. I'd ask your teacher which one they prefer for you to use, newtons. And so we're plugging in this equation here, so we got the 1 over 4 pi epsilon, and now we're multiplying by Q. Q is equal to 14.88 nanocoulombs, but we need to convert that into regular coulombs, so that's going to be 14.88, and now nano goes up to -9, so times 10 to the -9 coulombs. And then what is our X value? Our X value was 0.06 meters, or 6 centimeters, and then we're going to divide this guy by x squared plus a squared, and so that's going to be 0.06 meters squared plus, now we got our 1.353 centimeters up here, which is our R, which is our A, and we need to convert that to meters, so that's going to be 0.01353 meters squared, and raised to the 3 halves. Okay, so now we just plug all that into the calculator, and we'll get ourselves an answer, and the answer just happens to be 3.45 times 10 to the 4th newtons per coulombs. And it's positive, so that means we have an upward direction. And there you go. That is how you do that problem right there. And always remember that if you have a specific question that you need an answer to, that you can subscribe and submit me the question, and I'll be able to get it to you probably within a day or so.